Good morning, everybody. This is David Pott with the U.S. Fish and Wildlife Service. I'm the Climate Change Coordinator for the Pacific region. I wanted to mention that C3 is the Pacific Northwest Climate Change Collaboration, and we're a federal interagency group that focuses on information sharing and integration of efforts across agencies, landscape conservation cooperatives, and climate science centers. The series is co-sponsored by the Oregon Climate Change Research Institute and the Climate Impacts Group at the University of Washington. I'll go ahead and introduce Tim Mayer. Tim is the Water Resources Branch Chief for the U.S. Fish and Wildlife Service for both the Pacific region and the Pacific Southwest region, which includes California and Nevada. So Tim has a broad range of experience throughout the West. Tim has a bachelor's in forest resource management and then went on into his graduate work and received a PhD in environmental science and engineering. And he's been working as a hydrologist for the Fish and Wildlife Service since 1995. And Tim is going to present today a new regional study on landscape, stream, and channel factors that control summer stream temperatures, and talk a little bit about the role of climate in that as well. And this is a study that will soon be published in the Journal of Hydrology. So Tim, welcome, and take it away.
Okay, thanks, David. I assume everyone can hear me okay and can see the slides okay, so I'll go ahead and put up the title slide here. And everybody should be seeing the title slide that says Controls of Summer Stream Temperature in the Pacific Northwest on your screen. As David said, this talk is based on a paper that I just had reviewed and accepted and will soon be published in an upcoming issue of the Journal of Hydrology. This talk is going to be geared toward the non-technical side. I know we have a mix of technical and non-technical participants for these webinars. And so I'm going to keep it on the non-technical side. In fact, I was telling David I gave this presentation to my wife last night, and she understood most of it, and she is decidedly non-technical, although that doesn't keep her from being a pretty tough critic of my presentations. So anyway, if you have technical questions, I welcome those as well. We'll have plenty of time for questions and discussions at the end, and I'll even pause for questions halfway through or so. So when I say controls in the title here, I don't mean knobs and buttons on a panel. I'm using the term in the way that scientists use the term to refer to natural factors that change or modify or regulate stream temperature across the region. And these are factors like climatic conditions, landscape attributes, and stream channel characteristics. Now, if we were all to make a list together of the factors that affect stream temperature, there's some obvious ones that we might come up with as a group. For example, air temperature might be on the list. We probably all assume that areas with warmer temperature are going to have warmer air temperature are going to have warmer stream temperature. We might expect that areas with at higher elevation are going to have cooler temperatures, and we also might expect other characteristics like riparian vegetation cover and maybe the volume or flow of water in a stream and the shape and depth of the channel to be important too. So what my study is attempting to do is just to assess the relative importance of all these factors across the region. And I'm also trying to identify other factors that may be not as intuitive or maybe not as easily measured. So I'll say a little bit about how the work got started. It was motivated really by Dan Shively of the U.S. Fish and Wildlife Service. And as many of you may know, Dan recently collaborated with the nonprofit EcoTrust to develop an online aquatic ecosystem vulnerability assessment tool for the Pacific Northwest. And the tool is designed to help managers prioritize restoration and conservation efforts. So Dan came to me and he asked me for help in developing criteria to assess the vulnerability of streams to climate change And specifically, he was concerned with climate change impacts to discharge and to stream temperatures. And we quickly realized that while there was a lot of information and there were regional projections for stream discharge, there wasn't a lot of information on impacts to stream temperatures. And so I saw this as a great opportunity and an important research need, and so I started looking at this across the region. So one of the factors identified in that aquatic ecosystem vulnerability assessment tool was groundwater and the contribution of groundwater to streams. Within the last decade or so, there's been quite a bit of work by Gordon Grant and by others to suggest that groundwater is very important to stream flow in the Pacific Northwest. It has an important influence on stream flow in the Pacific Northwest. And I had done some work down in the Klamath in southern Oregon and northern California on groundwater-dominated streams down there, and I had seen some data down there that intrigued me and led me to believe that it was very important to stream temperatures as well, as an important factor for stream temperatures. So that's one of the factors that I looked at in this study pretty hard. And it turned out to be a pretty important factor, but it's not the only important factor. There are several others too. Again, the purpose of the study is to investigate factors that control summer stream temperatures across the region. And if we're thinking about this in terms of the vulnerability of the stream to future air temperature warming, we really need to know, at a very basic level, we really need to know two things. We need to know what is the stream temperature now, how cool or warm is the stream now, and how sensitive is it to air temperature increases or will be in the future. And those are described, those two aspects of stream temperature are described by what I'm referring to as the thermal regime and the thermal sensitivity. So if we increase summer air temperature by, say, 2 degrees in the future, what does that mean for stream temperatures? Do we expect stream temperatures to go up 2 degrees too, or do we expect there to be more or less warming? That's really what the measure of stream sensitivity is going to give us. But we also need to know, well, where are we starting from? Okay, how warm or cool is the stream initially or right now? Because we could have cool, and at one end of the spectrum, we could have cool streams that are not very sensitive to future air temperature warming, and those are probably not streams that we have to worry about. And on the other end of the spectrum, we could have warm streams that are very sensitive to air temperature increases, and those are streams that are going to get pretty hot pretty fast. So the important point that I want you to take away from this slide really is that there are a broad range of summer stream temperatures and summer sensitivities, and I'll show you more about that later in the presentation here. Okay, just real quick, I need to spend a lot of time on this, but why do we need to know this information? We need to understand controls of thermal regimes and stream sensitivities to develop habitat and natural resource management strategies, to anticipate and prepare for stream responses to climate change, and to identify conservation and restoration priorities. Okay, so this is a slide of the stream studies, the stream sites that I had in my study. There were 104 stream temperature sites across the Pacific Northwest that I looked at. These are unregulated stream temperature sites. They're mainly in Oregon, Washington, and Idaho. There's a couple in California. They're geographically distributed across the region as best I could do. And about two-thirds, or I should say about three-quarters of the sites in the study had data that was collected over the entire year, usually for several years in a row. Okay, but I'm referring to that as annual data. So it was collected not just in summer, but it was collected over the entire year. And the other 25% of the sites had data that was just collected in the summer season and not during the rest of the year. And I'm referring to that as summer data. Most of the sites did not collect air temperature locally. So for most of the sites, I derived a local air temperature record from a nearby climate station. I took the remote air temperature data, and I adjusted it using PRISM to come up with a derived local air temperature data set for the sites, for each of these sites. And I also compiled stream flow data for each of these sites, and I compiled several other landscape and stream channel characteristics, including factors like basin elevation, basin size, basin relief, basin slope, stream channel length, and stream channel slope. And this is all above the gauge. Okay, so I derived a lot of statistics for the area above the gauge in the watershed. Say a little bit more about the factors that are important to stream temperature. They can really be divided into three groups. They can be climate conditions, such as air temperature, solar radiation, evaporation, which turns out to be pretty important, as I'll discuss here a little bit further on.
Mute on.
Shape controls like elevation, latitude, longitude, geology, forest cover, relief aspect and area of the basin. And we can have stream channel characteristics that are important too, such as the stream discharge, the riparian vegetation, the length, slope, the width, the depth, the sinuosity, incision, substrate, and complexity of the channel. Now, I can't get regional information for all those factors for every site. So some of these I wasn't able to consider, but I'll kind of presage the results here, and I've underlined some of the important variables regionally for stream temperature. And I'll say more about that when we get to that section of the talk. So here's kind of an outline of how I'm going to present the results from the study. First, I'm going to show you some data from individual sites. I'm going to look at stream versus air temperature relationships from several different sites. And then I'm going to talk about the regional analysis, where I did group regressions and tried to look at this information regionally. And then last, I'm going to talk about using the summer stream to air temperature ratio as an index to assess stream temperature conditions at a site. So first, the individual sites analyses. The fundamental question that I'm trying to address in this part of the study is, what is the relationship of stream temperature to air temperature? We probably all intuitively expect that as air temperature warms, stream temperatures are going to warm as well. But what does that relationship look like? Is it linear? Is it nonlinear? Are there asymptotes? Does it vary from stream to stream? Does it vary from site to site within a stream? Does it vary regionally? Does it vary seasonally? And if it varies in any of those ways, then what are the causes of those variations? And that's what I'm trying to assess in this. And so the next several slides are going to be data of stream temperature versus air temperature at several sites. And I'm also going to show you various regression models to try to fit that relationship, that stream to air temperature relationship. Because ideally, if we can come up with an adequate regression model that describes that relationship, then we can extrapolate that model to higher air temperatures and say something about where stream temperatures are going to go in the future. And that really involves a measure of stream sensitivity. Okay, what I mentioned before, the thermal sensitivity of the stream to future air temperature increases. So this is the first slide I'm going to show you, and because I'm going to look at several different slides that are kind of formatted the same way, I'll explain this slide. This is weekly stream temperature to air temperature data. Covers the entire year, so this is one of the sites where data was collected throughout the year for several different years. And we have stream temperature on the y-axis, air temperatures on the x-axis. I've also shown a linear regression fit of these data, and I started all the linear regressions. I only included air temperatures greater than 0 when I did linear regressions of these data, because at sub-freezing air temperatures, the stream basically goes to 0 and stays there. So we don't expect any kind of linear relationship for air temperatures that are less than freezing. So therefore, the regression starts at air temperatures greater than 0. And you can see here the regression stats. I've given you the R-squared and the standard error. We have an R-squared of 0.95, a standard error of 1.48. Just want you to keep those in mind, because this is the same data set, and now this is fit with a nonlinear regression. Okay, this is an S-shape or sigmoid function, and several studies in the literature indicate that this is a better model for stream-to-air temperature relationships. And if you recall the regression stats from the previous slide, there is a slight, it's a small but a subtle improvement in regression stats when coming from the linear regression to the nonlinear regression. This is a little better R-squared. It went from 0.95 to here it's 0.97. And the standard area improved as well. It went from 1.48 to 1.39, and the smaller standard area is what is an improvement. So generally, I found this at all the sites that I looked at. Okay, there was an improvement in the regression statistics when I used nonlinear regression versus linear regression. So let me say a little bit of why that is. I talked about air temperatures below 0 and why the function kind of flattens out there at the lower end of air temperature ranges. Basically, the stream goes to 0 and it freezes and the temperature stays there. So we expect that flattening out in the lower end of the air temperature ranges on the right side of the plot. But at the higher end of the air temperature range, what happens there is at higher air temperatures, the air can hold more moisture, has a greater moisture holding capacity. And because the air holds more moisture, there is more evaporation from the stream surface. And evaporation is a cooling process. That's why we sweat when we get hot, so our bodies will stay cool. So in the same way, more of the energy goes into evaporating the water from the stream surface, and less of the energy, available energy, goes into heating the water temperature. So we see this flattening out at the upper end as well. Okay, there's less warming in the stream with a given increase in air temperature at the upper end. Now, another way I looked at that same aspect, okay, that difference at the higher end, was to compare regression slopes for the annual data, and in this case I looked at August data only. Okay, so I did 2 linear regressions, one for all air temperatures above 0, and then just looked one for just the data from August only. And in this case, you can see this is again still the Sprague River. We see the regression slope goes from 1.00 for the annual data down to 0.61 for the August regression slope. So another indication, this is another indication that there is this flattening out at the higher end of the air temperature range. And this was true, I did this for all sites where I had annual data available to do this comparison, and it was true for all sites. There was a significant decrease in the August regression slope compared to the annual regression slope at all sites. Okay, so now I'm going to move on to another site. This is also a site in Central Oregon. It's the Metolius River. Probably a lot of you know the Metolius River. It's a very highly groundwater-dominated system, and this is the same kind of plot. We've got stream temperature on the y-axis, air temperature on the x-axis. You see there's a lot less temperature range in the data for this site versus the Sprague River, the last site. And that's because it is such a groundwater-dominated system. So we see a much lower slope, a much smaller range of stream temperatures over still a pretty broad range of air temperatures. I've shown here the nonlinear regression fit. There was a small but subtle improvement in regression statistics for the nonlinear versus the linear regression, even for this site, although this is very close to linear. But there's still this flattening out at both ends of the air temperature range, on the left-hand side of the graph and on the right-hand side of the graph. And this is the comparison of the linear regression slope for the annual data for the Metolius versus the August regression slope. And you can see that the annual slope is about 0.24. It goes to about 1.12 for August. So even in this site, there's a suggestion that the stream sensitivity is decreasing at higher air temperatures. And this is quite important for climate change impacts, because if we're concerned about warming air temperatures during summer and stream temperatures going to extremes during that period, well, this says that streams are less sensitive to air temperature increases at that time of year. Okay, so I've got one more site I want to show you in the individual site analysis. This is the Minam River at Minam, Oregon. And this site, like a lot of the sites, I think about 85% of the sites, had or showed an effect of stream flow as well in the stream to air temperature relationship. And to show you that, what I've done here is I've highlighted in the solid circles there the high flow dates. Those are the dates where flow was in the upper 25th percentile of all flows for the period. And you can see that on those high flow dates, the stream temperature is cool. They mostly fall on the right-hand side of the graph, okay, on the lower side of the graph. And the stream temperature is cool relative to the air temperature on those dates. And so when there's high flows, and usually these are in this particular site, and a lot of sites it was in response to snowmelt, so this is April, May, June, July, the stream is not as likely to warm as with the air temperatures until the flow goes down, until the flows drop. And so for this, if I just take a nonlinear regression, and I don't include flow, I just do stream to air temperature with the nonlinear regression, I get an R squared of 0.87, and I get a standard error of 2.06. So not great. If I instead do a multiple nonlinear regression where I include air temperature and stream flow in the regression, I get an R squared, goes from 0.87 to 0.96, and my standard error drops to about half of the value. It goes from 2.06 to 1.06, so it's a very good improvement. And what I've shown you here plotted in the dashed dark red line there is just the equation for the stream to air temperature relationship holding flow constant. So that's what it looks like, and you can see that it does have that flattening out at both ends. It kind of captures it at the higher end as well. So as I said, many of the sites showed an impact of stream flow on the stream to air temperature relationship. About 85% of the sites, stream flow was just statistically significant when looking at annual data. For summer data, when I was just looking at August only, it was still about 60% of the sites where I had to include stream flow effects and do a multiple regression. And so the way I counted for stream flow was to do multiple regression. And I found that affected the value of the air temperature coefficient in the regression. And that coefficient is really what we're defining as the stream sensitivity, what I'm defining as the stream sensitivity. So it's important, if you want to get an accurate sensitivity value, to include stream flow in regressions, if that's the way you're approaching it. Okay, so kind of to return to the fundamental question I asked in the beginning of this section of the talk, what is the relation of stream temperature to air temperature? Air temperature explains most of the variance in stream temperatures at individual sites, but stream flow is important at many sites too. Nonlinear regression works best when considering stream and air temperature data for the entire year. Don't need to do nonlinear regression when you're just looking at August. That relationship can be linearized. But if you're looking at the entire year, a nonlinear regression works best. It works better than a linear regression, at least based on the regression statistics that I looked at. And the sensitivity to air temperature, as measured by the regression slope, is less in summer, and specifically in August, because that's the period I looked at, than at other times of the year. And this is due to the effects of evaporative cooling. As I said, this is important if we're approaching climate study impacts, climate change impacts study, and we're going to use sensitivity. Well, it's probably better to use regression slope based on summer data because of the lower sensitivity at that time of year than at other times of the year. So I just want to return and make one final point with respect to the individual sites. This is the August data and the August regressions for the 3 sites that I just showed you. Okay, plotted all together here. This is the same kind of plot we've been looking at. This is stream temperature on the y-axis, air temperature on the x-axis. And you can see that while August air temperature really doesn't vary very much among these sites, we have a pretty wide range of stream temperatures. We go from about a little less than 10 in the Metolius there in August to over 20, up to 25 almost in the Sprague in August, and stream temperatures. So a wide range of stream temperatures. And as you can see there, I plotted the values of the regression slopes too, and those are quite variable too. So the point with this slide is kind of the point I made in the beginning. There's a wide range of summer stream temperatures in streams across the region, and there's a wide range in regression slopes or stream sensitivities, summer stream sensitivities as well across the region. So with that, that's the end of that section of the individual site analyses, and I thought I would just pause here and ask if there are any questions on that before I go on and talk about the regional analysis and the stream temperature index. Are there any questions?
And this is David. I've got a lot of phones muted. So if folks do have a question, if they want to use the chat function on the WebEx screen.
Mute off.
So I'm almost done unmuting. So if you would prefer to just go ahead and speak up over the line, go ahead. Yeah, go ahead. Any questions out there?
If there are, David, I can just keep going. So.
Okay.
Oh, well, were any of the sites, I see a question, I saw, were any of the sites in wilderness areas, I think was the question? Yes. I don't recall how many, but they were primarily unregulated sites as best I could determine. And I did go through and look at the disturbance, the human disturbance index that Falcone et al. Provide for many of the sites. I wasn't able to get that information for all the sites, but I think about 80% of the sites or so had information on the human disturbance. And that index goes from about 1 to 29, I think, for the Northwest. And most of my sites were, well, they averaged around 8. Okay, but there were some up there in the teens and stuff, so there was, some variation. I wasn't looking at pristine sites. I was just primarily concerned with sites that were unregulated, but certainly some of these effects, some of these streams were affected by lack of riparian cover, by irrigation diversions, by grazing, that kind of thing. Okay. Any other questions, or we can keep going? I'll keep going. We'll have time at the end, too. not much more. So the now I'm going to kind of switch focus to the regional.
Mute on.
And I'm going to start looking at all the sites together as a group rather than individually. So I'm going to focus here on just the summer period and mainly the August data. When I say summer, I'm specifically referring to August. And in this part of the study, I attempted to explain or predict two things regionally. I wanted to know if we could predict August stream temperature regionally, and I wanted to know if I could predict August sensitivity regionally. And so keep in mind that for individual sites, air temperature describes, and stream flow, air temperature and stream flow describe most of the variance in annual and August weekly stream temperatures. So we know that air temperature does very well describing stream temperature at one particular individual site, but we also saw that there was a lot of variation in that relationship. So to do this, I have a lot of different August data points there for each site, and I just wanted one number for stream temperature and one number for air temperature. So I just simply took an average of all the August data for each site. And so, for instance, for the Sprague, I just averaged all the stream temperature, came up with an average, August average of 21 degrees C and an average air temperature of 17.4, and so on and so on. I did that at each of the 104 sites in the study area. So I had one value for August stream temperature and one value for August air temperature instead of a lot of different data points. So if we do that for all 104 sites, and then we plot the average August stream temperature versus the average August air temperature, this is what we get. We got a plot that looks like this. So again, August stream temperature is on the y-axis, air temperature is on the x-axis. Each of these symbols represents one of the 104 sites in the study. And you see there is a positive relationship, so that's good, as we expect. Stream temperatures go up with air temperatures, but there's a lot of variation in this relationship, and so air temperature is only explaining 20% of the variance in August stream temperatures across the region. And that's because there are a lot of other factors which are shown here implicitly but are not expressed in this plot or in this relationship. So can August stream temperature be determined from August air temperature regionally? The answer is, well, while air temperature explains much of the variability in stream temperature at any individual site, the relationship is site-specific and it can't be applied across the region. So variability in the relationship is due to a lot of other landscape factors and stream characteristics, which I'll explore next here. So what other landscape factors and stream channel characteristics are important for explaining the average summer temperature? And again, I want to explain the average summer temperature because this is part of the question that I'm interested in. Where are we at now? Okay, this addresses the where are we at now in terms of how warm or cool are we at a particular stream and, you know, across the region. I'm kind of just skipped ahead here to the final results. I did a lot of data exploration, looked at a lot of different explanatory variables, looked at different, sub-regions and smaller data sets, and trying to identify important explanatory variables. And I kind of consistently came up with these 5 explanatory variables being important, and especially the 3 that I've underlined there. But the 5 explanatory variables are the August air temperature, the base flow index, and base flow index is a measure of the groundwater contribution to a stream. So that's really how groundwater dominated a stream is. A higher base flow index means a more groundwater dominated stream. The stream channel slope above the site, so how steep or flat the stream is above the slope, the stream channel length above the site, and then the percent forested area in the basin. Okay. And those 5 variables explain about 72% of the variance in August stream temperature across the region. And generally, when we had warmer stream temperatures with warmer air temperatures and longer channel lengths. And if there was a high base flow index, or if there was a steep slope, or if there was a high percentage of forested area in the basin, then the stream temperatures were cooler. So kind of what you'd expect, for at least for some of those. The base flow index, I want to say more about that. That's the indicator of groundwater contribution in a stream. And I defined that several different ways in the paper and looked at several different measures of that. I'm not going to go into that here, but I can certainly talk about that more. But that turned out to be almost just as important, or even more so, than August air temperature when trying to explain the average stream temperature regionally. So summer stream temperature was negatively correlated with base flow index. That is to say, the higher the base flow index, the cooler the summer stream temperature. Groundwater is typically cooler than surface water. It's usually just a degree or two higher than the mean annual temperature at a site. And so higher base flow index means a cooler stream, basically. And we saw that with the Metolius data, if you recall, when we looked at the Metolius data. That was a very cool stream and that has a very high base flow index. In fact, one of the highest base flow indices in the study. Stream slope and length are important too. They were especially stream channel slope. And summer stream temperature was negatively correlated with stream slope, meaning that a steeper slope means a cooler stream temperature. In streams with high slopes, and often these are headwater streams, the water doesn't have enough time to equilibrate with atmospheric conditions, and so the water stays cooler. So that explains the inverse correlation or negative correlation, inverse relationship. The summer stream temperature is positively correlated with stream length. Generally, as you move downstream in a river or a stream system, stream temperatures warm, they increase. They say they probably have more time to equilibrate with atmospheric conditions. And so those two are positively correlated. Stream temperature was negatively correlated with percent forested area in the basin above the site. But this was not a very important variable. It didn't explain very much of the variance at all. I could have left it out. In fact, it dropped out in some cases in some smaller subregions. I think that percent forested area is really a surrogate variable for riparian vegetation cover, because it's likely that if you have a high forested area in the basin, you probably have good riparian cover too. Unfortunately, I didn't find regional coverage or regional information on riparian cover for all these sites, so I used percent forested area. And maybe that's why it wasn't as important. Maybe if I did have information on riparian vegetation, it may be a stronger variable. So again, air temperature, base flow index, and channel slope were really the most important explanatory variables for explaining average summer temperature or average August temperature. So now let's look at the same question. What other landscape factors and stream channel characteristics are important for explaining summer thermal sensitivity? So again, the summer thermal sensitivity is kind of the where are we going from here if air temperatures increase? How sensitive is the stream? And I tried to predict those regionally. I didn't do I wasn't able to do very well at explaining those. First thing I did is I tried to use the same explanatory variables, the 5 explanatory variables that I used for the previous question related to summer temperatures, average summer temperature. And of those 5, only base flow index and stream channel slope were statistically significant. And they only explained about 35% of the variance in August stream sensitivity across the region. So wasn't able to explain very much variance in stream sensitivity. I tried several other landscape attributes and really had very limited success. So I think there's a couple reasons for this. For one, it may be that sensitivity is controlled by local factors. Okay, that's one idea I had, and I don't have. These are regional attributes that I'm compiling, so I don't have enough information on very local factors at a site to be able to predict stream sensitivity. That's one explanation. The other explanation that I came across later in the study while I was actually going through some of the review comments from the reviewers, I went back to my sites where I had local air temperature data collected. There were about 10% of the sites that I looked at that had local air temperature collected at the stream temperature site itself. They collected both stream and air temperature data. And I went back to those sites and I pretended like there was no local air temperature there, and I derived a local air temperature record from a nearby climate station, just like I had done with all the others, and I used PRISM to adjust it and all. And then I looked at the stream sensitivity. I looked at a lot of things with that, but I looked at the stream sensitivity, and that seemed to be a little more variable depending on whether I used the observed local air temperature data or the derived local air temperature data. So I think the source of air temperature data may be leading to some variability and some noise in this stream sensitivity measure. And to tell the truth, it didn't seem as well constrained as some of the other factors that some of the other statistics I put together. Just seemed to be more variable. But anyway, one of the recommendations I made in the paper that came from that analysis was that I think it might be a good idea to collect local air temperature data at every site where a stream temperature is collected. It's a pretty easy parameter to collect. This is another logger, and then you have to put it into, some kind of appropriate housing and place it on the right side, the right aspect, and the right height and all. But it wouldn't be too much more work to collect air temperature. And I think that Washington State is doing that in many of their sites. So I think that's a good idea. I think that may help us constrain stream sensitivity in the future. So, okay, the last thing I want to talk about real briefly is the idea that the summer stream temperature to air temperature ratios provide some useful information for assessing stream temperature conditions at a site. So, this is a slide you saw before where I averaged my August stream temperature and my average August air temperature. And if I take each of those averages and I express that as a ratio, I come up with a fairly useful number. Okay, for the Sprague, the stream temperature air temperature ratio is 1.21. For the Minum, it's 0.93, and for the Metolius, it's 0.5. And I did that for all my sites, and the values were pretty systematic. In fact, I did this, after a while, I got to where I sort of had an idea what this ratio was going to be even before I calculated it, just looking at the site, looking where it was, and looking at the basin characteristics and that kind of thing. So it seemed to behave pretty consistently. The values for the 104 study sites that I looked at ranged from 0.5 to 1.26. And let's make sure that we're all straight what this means. A stream to air temperature ratio of 1 means the August stream temperature is equal to the August air temperature. And this seemed to be characteristics of streams that weren't too short, weren't too long, weren't too steep, were kind of moderate base flow index or lower base flow index, didn't have a lot of groundwater contribution in them. For ratios that are greater than 1, when the August stream temperature to air temperature ratio is greater than 1, that means that the August stream temperature exceeds the average August air temperature. And these were sites like the Sprague, as I showed you, some other sites down in that area. The Little Deschutes River was another one. They may indicate sites that are affected by irrigation diversions. They're low gradient, they're They don't have much riparian cover, kind of meandering through open meadows, and they're shallow, and so those sites seem to have ratios that are greater than 1, like 1.1 or 1.2, or those kind of values. Ratios that are less than 1 mean the August stream temperature is less than the August air temperature, and those seem to be characteristic of sites with either high groundwater contribution, so high base flow index, or sites that had very steep slopes and short lengths and were often headwater streams. So this is just kind of summarize that information in some plots. Here on the y-axis is the August stream temperature to air temperature ratio for all the sites, and I plotted these against base flow index on the top graph there, stream channel slope in the middle plot, and then stream channel length on the bottom. And you can see there's a negative relationship with the ratio for base flow index and also for stream channel slope. So that suggests that as you increase either base flow index or slope of the channel, the stream is cooler for the given air temperature. On the other hand, stream channel length has a positive relationship. As you increase channel length, you increase the ratio, meaning the stream gets warmer for a given air temperature. I will say with channel length, most of the action in the relationship is down at the shorter end there. You have short channels, short streams that have very low ratios, and you have some short streams that have higher ratios. Really, when you get to longer stream channels, most of the ratios kind of approach 1. So, and just to make clear, some of the outliers that you're seeing there can be explained by other factors that are not shown in the plot. So, for instance, in the top plot there, you see some of the high ratios around base flow index of 0.4 there in the middle of the top plot. Those are some of the streams I was talking about, the Sprague, the Little Deschutes River down in south central Oregon, with low slopes, long length, probably hammered too, hammered riparian cover and that kind of thing. On the other hand, if you look at the top plot and you look at the left-hand corner there, you see some really low values in the ratio there, some pretty cool streams relative to the air temperature in summer that are associated with low groundwater dominated systems, low base flow index. And those are streams that are, as I said, typically but not always high slow headwater streams, high slopes, short lengths. Okay, and some of the other outliers that you see in these plots too are explained by factors that aren't shown in the individual plot. So again, I think this might be a useful index for kind of rapidly assessing stream temperature conditions at a site. Generally for streams that are not very steep, not short, moderate base flow index, the ratio seems to approach 1. Interestingly, I had about 9 sites that were along the coast, and those all consistently had ratios that were above 1. They were like 1.2 to 1.26 or 1.1 to 1.26, something like that. So that says that the stream temperature is warmer than the local air temperature. And I think that makes sense when you think about these sites, probably if they're responding to warmer climatic conditions that are upstream in these coastal watersheds. The local air temperature at the coast is probably modified by the marine influence, and it's probably cooler. And since that air temperature value is in the denominator of the ratio, it drives the ratio up as the air temperature gets cooler. So it's kind of interesting. You might be able to use these ratios to kind of identify unique environmental conditions like that. Streams with high base flow index, so these are spring-fed streams or highly groundwater-dominated streams, they had ratios from about 0.5 to 0.7. And then streams with steep channels and short lengths had lower ratios too, meaning less than 1. They were about 0.6 to 0.9. And those with low gradient channels and longer lengths had higher ratios. So again, what information do these summer stream temperature to air temperature ratios provide? Well, I suggest in the paper that you may be able to use these to identify unique environmental conditions or point to potential restoration needs, or just kind of as a quick assessment of temperature conditions at a site. And so with that, I'm going to wrap it up here. So these are kind of the general conclusions from the study. Stream temperatures are strongly related to air temperatures and stream flow throughout the year. The stream thermal sensitivity to increasing air temperatures in summer is less than at other times of the year. The summer stream temperatures and sensitivities are considerably less in groundwater-dominated streams. So,
mute off.
And the degree of groundwater domination or degree of groundwater contribution to the stream is very important for stream temperatures. Some of the regional variability in summer stream temperature and sensitivity is also related to stream slope and the length. And finally, the summer stream temperature to air temperature ratio may provide information for a preliminary assessment of stream temperature conditions at a site. And with that, I'm done, and I will answer any questions. I see a question that flashed up on my monitor, something about have I split up sites to east side and west side, and yes, I did that. The only variable where that made a difference was the sensitivity. Kind of trying to predict the sensitivity regionally. I did better when I tried to predict sensitivity on the east side versus the west side, and that's east and west of the Cascades. And that was the primary geographic division that I looked at. I also looked at and talk about subgroups of the sites with respect to the coastal sites and their ratios. Some other sites in the paper, I discussed some of those sub-regional analyses. Didn't have a lot of time to do that in this talk, but I did do that. Are there other questions? And David, I guess you can maybe tell me if somebody's raising their hand on the...
Yeah, I have one question here about your data set and how many years and summers you have per site, maybe on average. I guess it probably changes.
Yeah, it really does. I mean, I took whatever was available. Most sites, all but, I think, if I remember right, all but 4 sites had at least 1 season or year of data. There were, I think, 4 sites where I just had a single year. And what happens is, if you have just a single year or a single season, you just have way fewer data points, and it becomes hard to develop significant relationships with regressions and that kind of thing. So usually I had 2, 3, 4, sometimes 10 or 15, occasionally even more, I think. I don't have that number offhand. Usually it was more than a single season or a year.
Okay, and then there's another question. How available are the data on base flow index, and where can one obtain those data?
Yeah, that's a good question. There is the USGS did grid base flow index, across the nation. So they came up with regional values of base flow index. I found in this study that they didn't do as well as a base flow that I defined myself using the flow statistics from the site. Okay, so I just went in and I just computed what I call a monthly base flow index. It's just the minimum, average minimum monthly flow over the average monthly flow for a site. And that's explained in the paper too, but I found that worked best. And there was some variability in the value computed that way versus what was derived by the USGS. I think they used some kind of graphical separation of base flow periods versus runoff and periods. I can't remember how they did it, but I did remember a comment that method that the USGS applied may not work as well in snowmelt-dominated systems where, if you get snowmelt over a long period of time, it may look like base flow to the software. statistical software trying to determine base flow index. So that led me to look at some other measures too, and I did find that the one that I derived from flow statistics, monthly flow statistics, was the best in the study.
Okay, a couple other questions. Did stream aspect or elevation contribute to predictability?
I didn't look at aspect. It's sort of hard to come up with aspect on a stream. It really is variable. I suppose there is something out there. I didn't find it readily available regionally for all sites. Elevation I did include basin elevation, and I included site elevation. Neither of those were significant, but I think that's because probably that's going to relate to air temperature, and because I was including air temperature instead of, it appeared, as the important variable instead of elevation.
So are you saying air temperature is a kind of a proxy for elevation?
Yeah, probably, I'm not sure if it's the proxy or elevation is a proxy for air temperature, but yeah, they're related.
And then
probably
one other
what
question,
we're trying to get at with elevation is the air temperature, ultimately.
Mm-hmm. So, Tim, one further question. Any further thoughts on how to use these data for prioritizing or selecting restoration activities?
Well, yeah, I guess it becomes almost a philosophical question. Do you go after the sites that and preserve those sites that look really good and look really cool and insensitive, and make sure nothing happens to them, and make sure access is provided for fisheries to those sites, or do you go to the sites that look like they're really sensitive, really hot, really sensitive, going to get worse, and try to put your efforts into that? And I don't have an answer for what. I suppose it's it's a combination, and then it also depends on where you're if you're trying to conserve fish species or that kind of thing. Where are they distributed? And how does it relate to the stream temperatures that are out there and the habitat that's out there? So I don't have a good answer for that, but that's a good question.
Okay, I don't see any more questions on the chat function. I maybe have time for one final question via phone line if someone would like to ask. Any further questions?
Where do we find that paper?
It's been accepted and reviewed and accepted by and revised and all that by Journal of Hydrology. So it will be appearing fairly soon. I think in the next several months, 3 or 4 months. I'm hoping that it gets published. I'm not sure what their turnaround is. I can also make sure that David gets it and distributes it to the D3 use group.
Yeah.
Yeah, and Tim, it may be good to just, if you could give your email address, people can follow up directly who are not members of C3.
Yeah, sure. My email address is my first and last name, so it's Tim_Mayer, and then it's at fws.gov. Pretty simple address. So certainly, if you have other questions or you want me to send you the paper when it comes out, I'd be happy to respond.
Great. Well, thanks, Tim. I'm typing your email address here. I did also want to mention that we have created a new YouTube channel, and the URL is kind of long. It might be simpler just to Google, YouTube C3, and you should find our webinars there. So that's kind of a new service. It'll probably take a week or two before we load up that video. And Tim, I wanted to thank you for a great and very thorough presentation on this topic.
Well, thank you.
For those that are members of C3, if you could hang on the line, we'll start a business meeting in 2 or 3 minutes. thanks everyone for joining today.
Kind of music. This is very cool. Holy cow. Yeah, Jenny Camper. Isn't that great? What kind of camera is this? GoPro. Well, some of that's his fancy camera. How does he do this, though? How does he do this? He's got a transition. He's got like a slide. That holds the eating right. Where are these people?